In In the last few lectures, we were examining how to incorporate correlations in balance equations, and we had done it for diffusion terminated transport, where the Nusselt number is equal to 2, and I said that you can do that as long as the time scale for diffusion, time scale for development of the temperature field around a heated object after the object is placed in a fluid at temperature T infinity. That time scale is small compared to the time for evolution of the temperature field. And we had used a Nusselt number correlation there in order to determine how to calculate the temperature as a function of time of that particular object. Okay. And we had done this for diffusion transport for the dissolution of a particle in a fluid, a similar concept. As long as the time for the diameter to decrease is much longer than the time required for the concentration field to develop around the particle, you can assume that the system is at steady state and use the steady state correlation in the balance equation for a time varying particle diameter. Okay. We had done that for forced convection as well, and I had summarized for you the characteristic length scales at high Peclet number for forced convection. And you can use the characteristic length scale, the characteristic time scale in all of these will go as the length scale square divided by the diffusion coefficient, which whether it is d for mass diffusion or alpha for thermal diffusion. Okay. And this diffusion, and so long as this time scale for development of this temperature field around the object, in that case there is a rapid downstream flow of the fluid around the object, and any mass that is diffusing perpendicular to the surface or any energy diffusing perpendicular to the surface gets rapidly swept downstream, and therefore the disturbance to the temperature or the concentration field is restricted to a thin region close to the wall. And I just stated for you what that characteristic length scale of that thin region is for different configurations, for flow in a pipe, for flow past a film, and other such configurations. And we had solved some problems using correlations. Okay. If you recall, we had used a particular correlation for convection, where the expression for the Nusselt number here, okay, was given by the correlation, which is 0.992 times P power 1/3, okay, for natural convection. I should note that these correlations are only indicative, they are not comprehensive. Okay. You could, for example, use the Whittaker correlation or the Ranson-Marshall correlation here as well. Okay. The Whittaker correlation, for example, is that Nusselt number is equal to 2 plus 0.6 R e per half P r power 1/3. Okay. You could use this as well in this case, okay, depending upon the situation. Okay. In order to get an estimate for design purposes, you would solve the problem using both correlations and use the more conservative estimate in order to guide your design decisions. And similarly, for specific unit operations, for specific equipment, there will be, in that particular domain, there will be correlations that have been formulated and tested, and you could use those correlations. However, the procedure, the calculation procedure will be exactly the same as that I have used here. You may use more complicated correlations, but the same procedure can be used provided the same conditions are satisfied. That is, the diffusion time is much smaller than the time scale for evolution of the temperature or the concentration at the surfaces, okay, for time varying boundary conditions, or the length scale is much smaller than the characteristic length of the object. The length scale for diffusion at high Peclet number is much smaller than the characteristic length of the object, in case of spatially varying configurations. In that case, you can use a correlation that is derived assuming that the temperature at the surface and the temperature far away are constants. Okay. So, as long as that principle is satisfied, you can use other more specialized correlations as well in the same balance procedure. So, I had gone through diffusion dominated transport and natural convection, and finally, I was considering I had gone through diffusion dominated transport and forced convection where the velocity field is specified, and I was considering natural convection heat transfer. Okay. In this particular case, there is a difference because the Grashof number depends on the temperature difference. Okay, and we are usually considering the case where the Grashof number is large. When we had done dimensional analysis, I had defined for you the Grashof number and estimated it in everyday situations, and it turned out to be very large in the range 10 power 4 to 10 power 9. In that case, the thickness of this boundary layer where the presence of the object causes a disturbance to the temperature and the velocity fields, that scales as GR power minus 1/4. Okay. So long as Grashof number is large, the thickness of this is much smaller than the characteristic dimension. Okay. So, that is the diffusion length. The diffusion time will be LD square divided by alpha, or LD square divided by the diffusivity for mass transport. So, I will not go into the details of the calculation. I will just indicate to you what are the differences in the calculation between this problem and the natural convection problem. Okay. In the natural convection problem, you recall for heat transfer from a sphere, this is what we had got for the temperature profile. Okay. This is what we had got for the temperature profile. Okay. So, I can use that temperature profile as well in this particular case, okay, for a sphere of diameter d. Okay. So, what I will do is that I will take this temperature profile and incorporate that the transport coefficient into that temperature profile. Okay. So, I will just show you indicate to you how that is done. Okay. If you recall, we had a sphere, okay, a steel sphere of a particular diameter in a fluid. Now, in this case, it is a natural convection problem. So, we have the temperature of the sphere as Ts and the temperature far away from the sphere as T infinity. Okay. And we have to find out what is the rate of convective of natural convection heat transfer. How does that natural convection alter the steel temperature, the temperature of the steel sphere as it cools in time. And the balance equation, if you recall, was m Cp dTs by dt, okay, is equal to minus pi d square times q average. Okay. The mass of the sphere was pi d cubed by 6 rho s density Cps of the sphere dTs by dt is equal to minus pi d square into the average flux, okay, K of the fluid into Ts minus T fluid. Okay. So, I am assuming that this temperature far away is what is called as Tf, okay, divided by d, okay, times the Nusselt number. Okay. So, I have expressed the flux, average flux in terms of the Nusselt number as K delta T by d, where delta T is the difference in temperature between the surface of the sphere and the fluid far away. Okay. And from this I will get dTs by dt is equal to minus 6 Kf into Ts minus Tf, the Nusselt number, divided by d square into rho s into Cps. So, that is the expression for the temperature, the rate of change of temperature with respect to time. Okay. And in this expression for the rate of temperature with respect to time, I have to substitute the effect of the Nusselt number correlation. Okay. Note that the Nusselt number is equal to some constant, okay, is equal to some constant times Grashof number to the 1/4 power. Okay. In this particular case, since the mass of the sphere is a constant, okay, I will just retain the mass of the sphere itself, whereas in the previous cases where diameter is varying, I had to change the mass of the sphere. Okay. So, this is the expression, and in this I substitute the Nusselt number is equal to rho square. Okay. This is the density of the fluid square, okay, G beta into Ts minus Tf, okay, into d cubed divided by the viscosity square, okay, whole power 1/4, okay, into some constant which is a function of Prandtl number. Okay. So, the Nusselt number is equal to Grashof number power 1/4 times the Prandtl number, and I have just substituted for the Grashof number here. Okay. In this particular case, I just substituted for the Grashof number. However, the Grashof number does contain within it the temperature difference. Okay. The Grashof number does contain within it the temperature difference, and therefore, the right side is not linear in the temperature. Okay. The right side of the equation is not linear in the temperature, because the Nusselt number does contain within it, okay, a temperature difference. It goes as the difference in temperature to the 1/4 power. Okay. It goes as the difference in temperature to the 1/4 power. So, I have to incorporate that into the equations. Okay. So, if I incorporate this into the equation, I will get dTs by dt is equal to minus 6, okay, times C of PR Kf, okay, divided by d square rho s Cps, okay, into this Grashof number now, okay, to the 1/4 power. Okay. So, this Grashof number to the 1/4 power, I note that this Prandtl number is a material property. So, it is a constant for a particular fluid. The Prandtl number is equal to Cp mu by K, which is a constant for a particular fluid. So, I can just incorporate that into the constants. And then I have rho f square g beta d cubed by mu f square whole power 1/4 into Ts minus Tf whole power 5/4. Okay. So, I have a factor of Ts minus Tf here and Ts minus Tf power 1/4 here. Okay. So, that becomes Ts minus Tf power 5/4. Okay. I can scale, right, define a scaled temperature Ts star is equal to Ts minus Tf divided by the initial temperature minus Tf. Okay. So, let us say that the sphere had an initial temperature Ti and the temperature at any time t was Ts, then I can define a scaled temperature, okay, Ts minus Tf by the initial temperature minus Tf. Okay. And you can express this implies that Ts is equal to T star into Tsi minus Tf plus Tf. Okay. Okay. So, for the left side I will use this expression. Okay. And if I substitute this into the equation, I will get that Tsi minus Tf, okay, dt star, okay, of the sphere divided by dt is equal to minus 6 Cpr Kf by d square rho s Cps into Tsi minus Tf, sorry, I should take this here. Into T star power 5 by 4 times Tsi minus Tf power 5 by 4. Okay. And you can see that this Tsi minus Tf will cancel and you will just get Tsi minus Tf power 1/4 on the right side, and the temperature dTs star by dt is equal to minus of Ts star power 5 by 4 by the characteristic time, okay, where the characteristic time, okay, is equal to d square rho s Cps by 6 CFPR Kf into mu f square by rho f square G beta into Tsi minus Tf, okay, times d cubed power 1/4. Okay. So, the characteristic time in this case actually depends upon the initial temperature difference between the sphere and the fluid. Okay. And if you express this in terms of this characteristic time, you get a linear differential equation in for the temperature field. Okay. This is not a linear equation, this is an ordinary differential equation which can be solved, okay, to get an expression for the temperature. Okay. The difference I am trying to point out here is that the time scale actually depends upon the temperature difference initially in this case if you scale the temperature this way. Okay. And you can of course solve this equation to get dTs star by d by Ts star power 5 by 4 is equal to dt by Tc. Okay. And you know that the integral of dx times x power alpha is equal to x power alpha plus 1 by alpha plus 1. Okay. In this particular case, alpha is equal to minus 5 by 4. Okay. So, that's the expression for the integral. Okay. So, alpha plus 1 will be minus 1 by 4. Okay. So, you will get 1 by alpha plus 1 will be minus 4. Okay. You get minus 4 T star power minus 1 by 4 is equal to T plus a constant, T by Tc plus a constant, and then you impose the condition that at T is equal to 0, T star is equal to 1, because T star is the scale temperature, the difference between the instantaneous temperature and the fluid temperature divided by the initial temperature and the fluid temperature. So, because of that you will get T star is equal to 1 at T is equal to 0, and my final expression for the temperature field is going to be equal to I should have a negative sign on the right side here. Yes, I should just put a negative sign on the right side here. Negative sign on the right side here. Okay. Because you recall that I have minus T by Tc here. Okay. Yeah, I have a minus sign here. Okay. So, at T equal to 0, T star is equal to 0, and if I impose that condition, I will get that the final solution as 4 into T star power minus 1 by 4 minus 1 is equal to T by Tc, which implies that T star is equal to 1 plus T by Tc power minus 4. So, that is the final solution in this case. It is not an exponential anymore, it is a power law. Okay. So, this expression can be used to evaluate the temperature of the sphere as a function of time. The scale temperature that has been defined in this manner. Okay. So, this was just to point out the difference that you have in the case of natural convection, because the convection velocity depends upon the temperature difference, and because of that the Nusselt number, which is proportional to Grashof number to the 1/4 power, contains within it the temperature difference, and that has to be incorporated in the balance equation. In this particular case I did it by scaling, okay, so that the left and the right side of this equation have the same dimension. Okay. T is dimensionless, so the left and right side have the same dimension. So, that scaling was used in order to find out the expression for the temperature. Okay. And I should note that this is Ts here and this is Ts. Okay, that is the scaled temperature. Yeah. So, this is how you would solve natural convection problems, time evolution, by incorporating the correlation in the balance equation. Okay. And finally, we will solve a spatially varying time problem where the system is at steady state, but the temperature varies spatially. Okay. Okay. So, this is the heat transfer from a fin. Okay. Fins are often placed on walls of heat exchangers, okay, in order to enhance the heat conduction. The fin is made of a material which has a very high thermal conductivity. Okay. It is made of a material with a very high thermal conductivity, and because you have a fin on the wall, the surface area for heat transfer, effectively the temperature everywhere on the fin, because it has a very high thermal conductivity, effectively the temperature everywhere on the fin is the same as the wall temperature. Okay. And because of that you have enhanced thermal conductivity, because it has increased the area for the surface area for heat transfer. Okay. And in this particular case we have a wall temperature at the surface. Okay. I will call that wall temperature as T naught, T is equal to T naught on the surface, okay, and T is equal to Tf far away. Okay. And as the distance varies, so I'll take this as the x direction, okay, the distance along the fin as the x direction, and the cross sectional area I'll call it as ACS, okay, and the total length of the fin will be called as L. Okay. L is the total length. Okay. And along the length the temperature decreases, because you can see that there is natural convection that is happening. Okay. As you go along the length of the fin, due to natural convection, heat is being transferred from the fin to the fluid. Okay. Heat is being transferred from the fin to the fluid due to natural convection, and because of that the temperature decreases as you go along the length of the film. And what we would like to find out is, at steady state, what is the temperature profile along the length of the film. For that we have to do a balance. Okay. We take a cross section of the film, okay, at a particular location, okay, a small distance delta x, along the length, and do an energy balance. The energy coming in from the left is equal to the energy going out from the right, as well as the energy that is being convected due to natural convection from the surface of the film into the fluid. Okay. Energy entering in from the left, okay, is going to be equal to the flux q x at x times the area per unit time. Okay. The energy entering in from the left is the flux at the location x times the area, the energy entering per unit time. The energy leaving on the right side is qx at x plus delta x times ACS. Okay. And the energy that is leaving due to natural convection from the surface of the film is going to be equal to minus q average flux due to natural convection, right, times the surface area, okay, the surface area of the film. Okay. The surface area of the film is going to be equal to the wetted perimeter times delta x. Okay. The surface area of the film is equal to the wetted perimeter times delta x. Okay. Delta x is the width of this region, Okay. This is delta x, and the wetted perimeter is this entire perimeter of the cross section. Okay. That is the wetted perimeter. Okay. So, this has to be equal to 0 at steady state. This has to be equal to 0 at steady state. You can divide throughout by delta x, divide throughout by ACS. Okay. So, Qx at x minus Qx at x plus delta x divided by delta x, okay, minus QAV wetted perimeter divided by cross sectional area is equal to 0. So, that is the balance equation. Note that the cross sectional area by wetted perimeter is equal to the hydraulic radius. Okay, for long objects, the cross sectional area by wetted perimeter is equal to the hydraulic radius. Okay, by the wetted perimeter is equal to the hydraulic radius, which is equal to the equivalent diameter by 4. Okay, which is equal to the equivalent diameter divided by 4. Okay. The first term on the left, in the limit as delta x goes to 0 is equal to minus d of qx by dx. Okay. That is the first term on the left, in the limit as delta x goes to 0. You convert from a difference equation to a differential equation, and the second term is equal to minus 4 QAV by the equivalent diameter is equal to 0. For the first term, I can substitute Fick's law. Okay. Qx because the heat transfer is taking place by conduction within the film. Okay. So, the Fick's law is that Qx is equal to minus the conductivity of the solid times dt by dx. Okay. Qx is equal to minus the thermal conductivity of the solid times dt by dx. Okay. So, therefore, this is K solid dt by dx, okay, with a plus sign because the flux is negative is proportional to negative of the temperature gradient. And for this I can write 4 by dE, okay, into QAV. The average flux I can express in terms of the Nusselt number correlation, right, that is the fluid temperature, fluid conductivity into the temperature on the surface of the fin minus the fluid temperature, okay, by dE, okay, into the Nusselt number is equal to 0. I made a mistake here. It should be the second derivative. It should be the second derivative because the flux itself is proportional to the first derivative, and here I have the derivative of the flux. Okay. So, this thing ought to be the second derivative. Okay. This thing ought to be the second derivative. And I take the second term on the left to the right side, and I will get d square t by dx square is equal to 4 by dE square kf by ks into t minus tf into the Nusselt number. Okay. And this I can write it as 4 by dE square kf by ks t minus tf, okay, into the Nusselt number. The Nusselt number is equal to a constant which depends upon the Prandtl number times rho f square g beta t minus tf into the equivalent diameter cubed by mu f square whole power 1/3. Okay. And once again you have a t minus tf power, I am sorry, this should be 1/4. I have a T minus Tf power 1/4 on the right side, right. So, therefore, I can define a scale temperature, okay. That is, you know that the temperature at x is equal to 0 is equal to T naught, and if you assume that at the other end of the film T is equal to TL, okay, and I will assume that the temperature gradient at the other side is 0 because there is no flux coming out of the other side. It is an insulated end of the fin, okay, on the right side, okay, and that temperature is TL. Okay. So, I can define a scale temperature as T star is equal to T minus Tf by T naught minus Tf, okay, and express this temperature in terms of T star, okay, and I will get d square T star by dt dx square is equal to 4 by dE square kf by ks, okay, into C of PR into rho f square g beta T minus Tf. Okay, so, this will be T naught minus Tf into dE cubed by mu f square, okay, into T star power 5 by 4. Okay, when I express this temperature in terms of T star, I will get that T is equal to T naught minus Tf into T star plus Tf. Okay. When I substitute that into this equation, I get a T naught minus Tf on this left side here. Okay. I will get a T naught minus Tf on this left side here. On the right side, I will get T naught minus Tf to the 5/4 power. Okay. So, when I cancel out, I will just get T naught minus Tf to the 1/4 power in the expression for the Grashof number, okay, which is T star power 5 by 4 by Lc square. Lc is the characteristic length for variation of temperature along the fin. Okay. So, Lc is the characteristic length for variation of the temperature along the fin, and Lc square is equal to dE square by 4 Ks by Kf 1 by C of PR into mu f square by rho f square g beta T naught minus Tf dE cubed, okay, whole power 1/4. Okay. And you can see that this is equivalent to dE square by 4 into Ks by Kf 1 by C of PR into 1 by Grashof number based upon the initial temperature, based upon T naught to the 1/4. Okay, it is dE square times this entire thing. Okay. And the requirement that the length scale for variation has to be much larger, has to be the length scale for the characteristic length has to be much larger than the equivalent diameter, which is the characteristic length for the object. Okay. It reduces to this condition that Lc square, the length scale for variation along the x direction, has to be much larger than this equivalent diameter square. In that case, I can use a continuum approximation. Okay. And in this case, you can see that I have a Grashof number power 1/4 in the denominator. On the other hand, Ks by Kf is actually very large, okay, because the conductivity of the steel or the material that is used for making the fin is actually much larger than the fluid thermal conductivity. Okay. So, this is the characteristic length, and then you can solve the equation and get an expression. You cannot in this case get an analytical expression, but up to this stage, up to calculating the equation for the scale temperature field, this can be done analytically. Further, you can still do some simplifications using some manipulations, which I will not go through in this lecture, just to show you how the correlation can be used in the balance equation to derive an equation for the variation in temperature along the length of the film. Okay. So, So, this is an example where you have the characteristic length, okay, which is d squared times some function being large compared to the length scale for diffusion. Okay. The diffusion length in this case is equal to gr power minus 1/4, okay, times the diameter square. Okay. So, therefore, in this case if the Grashof number power minus 1/4 times the diameter, the equivalent diameter is much smaller than the characteristic length, then you can use a continuum approximation. We will examine this a little more briefly in the next lecture before we go on to another problem, which is the transport in a fact column. We will see that in the next lecture. I will see you then.